In this video I'm going to talk about projectiles, and I'm going to test out my ability to edit a video. We're going to have a little chat, then I'm going to do an experiment, and then I'm going to talk through some theory of it up on my iPad. I'm going to try and merge those three videos together and we'll see what happens. But projectiles. So anything that has been launched in some way, so you could take this pen and throw it, as soon as it has been released, it's going to fly through the air, and that object is dictated by, the motion of that object is dictated by the rules that we'll study in this whole idea of projectiles. It is a projectile. It doesn't have any method of propulsion once it's in the air. It's not got a motor pulling it along or anything like that. The only force acting on it is gravity. It can be going up, it can be going down, you can be throwing it down, the same rules will apply. First concept we're going to look at then is you have a cliff. Here, it's not the best, in fact my other pen is better I think. You have a cliff, and if we were to fall off the cliff into the sea and dive in, we'd fall down, wouldn't we? And from our free fall study, we can understand a little bit about how long that would take. We can identify that at the top, u is 0 meters per second. The acceleration is gravity at 9.81 meters per second squared. And we can either know the height of it or the time of flight, and that will allow us to calculate everything else. Those would be our three knowns. Yeah? So if we said that this cliff was 28 meters high, then we have our three knowns, so we could calculate time and we could calculate how fast will we go when we hit the water, and therefore be able to make a judgment about whether that is a safe height to jump from or not. In projectile motion, within the IB, typically, always our calculations won't involve air resistance. In the question, it will say that air resistance is negligible, not relevant, not to be calculated. Sometimes at the end of those IB questions, they will ask you to consider the difference from your calculated value if air resistance was included. So you're just basically going to be saying something like, it's going to reach terminal velocity, or it's going to go slower so it won't go as far. Something like that. So that's all you have to do for air resistance. I've seen an imagery one where I've seen a projectile launched, and that's our symmetrical pattern. And then they said, okay, what would the projectile path be like if air resistance was included? Well, it wouldn't travel as far, would it? It'd get less distance, and maybe our flight would look slightly different because the horizontal motion would have been slowing down throughout. So that's all they're going to ask you to do. That's the hardest I've ever seen. This so far is free fall and covered in my previous free fall video. To make it a projectiles one, we're going to change it ever so slightly. We're going to think about our object moving forwards. And this is a concept we've got to get our heads around. This is the bit that confuses us. If we were to run and jump horizontally, what would we notice different about the flight? Is there a light making it really hard to see? Yeah. If we were to run and jump horizontally, what would we notice different about the motion of the object or the person? We'd land further away. That's probably something you've said. And most commonly, people will say it would take longer. You'd be in the air longer. So time would be, we still don't know it, but time would be larger. That's the most common thing. Well, that's not correct. what we're going to do is I'm going to show you an experiment where on my desk here I'm going to take let me do it. I'm going to take a ruler, just a simple metal ruler, and I'm going to take 2 of the little 10 gram masses that we use in science, and I've got the ruler at an angle, and I'm going to set it up so that one of the coins is going to be pushed out and one of them is going to be allowed to drop straight down, and we are going to compare the difference. So let me just show you this setup a little bit. So let me get a decent light. So here we have our setup. We have one coin that's going to be pushed straight out. This coin is going to be pushed straight out, and this coin is going to be allowed to drop when I spin the ruler. And we're going to do a slow motion video of the coin going out and the coin going down, and we're going to look and analyse that motion and compare that motion. That's going to be the next, hopefully, seamless integration into this video. Here we go then. So you just saw a nice slow-mo video of a coin being launched off a table, one straight down and one like straight outwards. And so if you go back and pause the video when you see that happening, you'll notice that it's hard to do, but I had to play with it and it is achievable. The coins are always horizontal with each other. As a little bit of time goes by, it's further down, but this one has also moved the same distance down. Yeah? Even though this coin has moved across, from a downwards perspective, it's done the same distance, and that means that the coins strike the ground at the same time, not the same point, they're apart, but they strike the ground at the same time. So the time of flight, the time to fall, is the same, which is a little bit counterintuitive, isn't it? You wouldn't expect that to happen. And that is to do with this idea that the only force acting on it is gravity. Yeah? And in both scenarios, from a downwards perspective, the initial velocity is 0. From a cross perspective, there's a 0 for the one that went straight down, and then there's a 0, there's an initial velocity of, I don't know what it was, let's say 5, right? There was a value, a non-zero. Sometimes this is referred to as a non-zero value. They're basically saying it has a value, but it doesn't really matter what it is. So the coin was flying across, and the one going straight down, they fell at the same rate. Gravity for both of them was 9.81 meters per second squared, which meant it took the same time to go down for both of them. Yeah? The only difference was one of them was able to move across as well. And what this is teaching us, what this identifies to us, is a very key concept, and that is that the horizontal and vertical components of motion are independent of each other. So whatever you do to the horizontal, it has no effect on the vertical and vice versa. So this change, where I've been doing it in blue, is all about the horizontal. It has no effect on the vertical here. Yeah? And so all we need to be able to do is process them separately. So just like with free fall, we could calculate the time it takes for it to fall. I know that my desk is 1.2 meters high because I've had to use that for an experiment previously. I know that the initial velocity down is 0 meters per second, and I know that the acceleration is 9.81 meters per second squared. This will allow me to use my SUVAT, or my equations of motion, to find both the time and the final velocity. Yeah? I can do that. I think we'll do that on a separate page. Oh, I've only just started using this, so I want a new table. Okay, maybe not. To be fair, that saves me writing these out again. Oh, it's clever how it's speed dependent for the eraser. It's very clever. This is Microsoft Whiteboard. I use a little Apple iPad to do these with an Apple pen. It's fantastic. I don't know why anyone has a laptop anymore. Anyway, so let's find t. Okay, we've got our 3 knowns, and we've got our 1 unknown. It's any equation of our equations of motion that doesn't involve v. So we have s equals ut plus a half at squared. That's what we're going to use here. U and t, u is 0, so ut is 0. So we can say s equals a half. I'm going to write g instead of a, gt squared. Some people prefer to keep it as a, and some people like to identify that it's 9.81, it's g. It's kind of irrelevant. Yeah. Then we'll do some rearranging. 2s equals gt squared. 2s over g equals t squared. 2s over g equals t, as long as you square root it. So that means square root of 2 times 1.2 over 9.81 is going to give us t. Let's grab my calculator. I get an answer of 0.49. Oh, what am I writing? 0.49 seconds. Okay, you hopefully get that. It's 4946 blah blah blah. But as you can see from my question, this is 2 significant figures, so I shall use 2 significant figures here. Eraser. The next one. Let's do. Let's find v. You could do any of the other equations now. I'm going to use one that doesn't have t in it, because I'm going to not trust my own answer. I'm going to use v squared equals u squared plus 2as. V equals the square root of u squared plus 2as, but then u is 0, so it's the square root of 2as, which is the square root of 2 times 9.81 times 1.2, which means it is 2 times 1 times 1.2, answer 4.9 meters per second. There we go. So we found out everything about our projectile flight now, yeah, in terms of its vertical movement, yeah? The time that it's in the air for is the same. So if we go and consider the horizontal now, we can look at our projectile and we can say, well, it does that. So how far has it come? Yeah? Well, we know that t is the same. We know that t is 0.49 seconds. Horizontally, there is no acceleration, is there? The only acceleration it experiences is gravity, which is down. So a equals 0 meters per second squared, right? Which means we can use the old-fashioned speed equals distance over time, or velocity equals displacement, learn to spell, displacement over time taken, yeah? All we need to know is the velocity. I hypothesized earlier that it was 5, so if we wanted to find out how far it go, v equals s over t. Well, s is going to be vt, which is, I said it was 5 times 0.49. Yeah, so we just do that on our calculator. 5 times 0.49, 2.45 meters would be how far I think it would fly. That's all right, cheers. Just handing over my laptop for some work. Yeah. So that's all we have to do for both those components. So let's look at a more complex scenario like you would experience in an exam. Just going to erase all of this. So they give us. Actually, before we think about a complex scenario, let's think about something that's really, really useful. So there's a couple of key points. A is often g. You might remember that from the equations of motion lesson anyway. In many scenarios, u is 0, and do look out for that because it won't tell you in questions. You will be expected to identify that from the question. If anything is being dropped, u is 0. If anything's starting from rest, u is 0, or going to rest, then v is 0. In projectile motion, if we throw something up, then it takes a very distinct parabola shape. I don't know why I did dots for that. But what we can identify from that is if we find the peak, right? First off, it's symmetrical both ways. So whatever the u is here, it's the same v there. Whatever time it takes to go up, that's the time it takes to go down. However high it goes up is the same that it goes down. And also at the top, for a split second, that's clever. For a split second, the motion is only horizontal. So at the very, very peak, vertically, so up and down, vertically speaking, the velocity is 0. Which means if you were to consider only up, then you'd say v equals 0 vertically. Or if you were to only consider down, you'd say u equals 0. A really useful feature for us. Right, let's... Oh, hang on. I've just identified that I can scroll down. In fact, yeah, this is just a huge free board. This is really good, and I can zoom out. Yeah, there we go. I'm just going to have a swig of water. It's a bit dehydrated today. What else next? Okay, let's do some scenarios then. let's use this first scenario. Let's throw a ball. Let's launch a ball upwards. Let's have an initial velocity of 15 meters per second at an angle of 20 degrees from the horizontal. Okay. From your studies in mathematics, you know Sokotoa, as I call it, or silly old Harry, Corte herring, two offer alley. Here we have a right-angled triangle because this is horizontal, this is vertical. So we can break down our flight, the initial motion of the object, we can break it down into horizontal and vertical components. And then all we do at the very end is we'll have the object coming down, we will put it back into horizontal and vertical components. We already know that this is going to be 15 meters per second. Okay. But we don't know a lot else, do we? We have given an initial velocity and a launch angle. From that, we can say that horizontally, acceleration is 0. Whoops. Vertically, acceleration is g, which is 9.81. That's it. We can identify at the top that there is only that the velocity vertically is 0 and the velocity horizontally is a non-zero value. So let's calculate a few things. We can calculate all sorts about this flight. We can calculate the maximum height that it reaches. In fact, I'm just going to draw that on here. We can calculate the maximum height that it reaches. We can calculate how far it will go. So we've got S horizontal and S vertical. We can calculate the time of flight. Yeah. So let's go ahead and do that. The first step is breaking it down into U of 15 into horizontal. So horizontal is going to be this one, which means it's hypotenuse and adjacent. Hypotenuse and adjacent is cosine. So cosine 20 equals equals the velocity horizontally, but it's u, isn't it? So let's be disciplined. It's u horizontally over 15. Yeah. So u horizontally is 15 cosine 20. I'm actually not going to calculate a numerical value for that. I'm going to leave it like that, where it's not got any decimal places to it. Vertically speaking, I've selected a different pen. Vertically speaking, sine 20 is the vertical velocity over 15. So uv equals 15 sine 20 meters per second. I don't actually like that pen very much. Yeah. So we know our two values here. We know that this is 15 cosine 20 and that this is 15 sine 20. Okay, we know those aspects about the end one as well. Let's consider the horizontal I wrote first. So let's consider horizontal. Yeah? Let's use that for... No, let's do vertical. Yeah, let's do vertical. Use the blue pen. Vertical. S. And we'll do T from the vertical. We know vertically speaking. Let's just do the up then. Okay, so up only. We know that A is G 9.81, and we know that U is 15 cosine 20, and we know that at the top V is 0 meters per second, yeah? Okay, which means we've got three knowns. Key point though, look, the acceleration is in the opposite direction to the motion, so we should give one of those a negative symbol. Or we can consider the downward motion, in which case, if we consider the downward bit, U is 0, V is 15. So let's consider down only, because I do love it when U is 0. Everything is so much easier. So let's do S. Oh no, hang on, not S. Let's do V squared equals U squared plus 2AS to find S. Let's rearrange that. U is 0, so we get rid of that. So V squared equals 2AS. So S equals V squared over 2A, which is 15 cosine 20 squared over 2 times 9.81. Calculator. 15 cosine 20 squared divided by 2 times 9.81, which is 0.68 meters. It's not going to get very high. Okay, now we can do T. I'm going to avoid using my own answer, so I'm going to do V equals U plus AT, that equation, and rearrange it. V minus U equals AT. V minus U over A equals T. So T is V 15 cosine 20 minus 0 over 9.81. 15 cosine 20 divided by 9.81. 1.4 seconds. But this was for down only. The up is the same, so total is twice that. Yeah? So that's given us everything we need to know about the vertical motion. Now we're going to consider the horizontal motion. This is simply V equals S over T, isn't it? Speed equals distance over time. We want distance, so distance equals velocity times time. Well, the velocity was, or T is 2.8, we've just established that. And V is 15 sine 20. So S is 15 sine 20 times 2.8, which is 15 sine 20 times 2.8. I get 14.4 meters is the horizontal movement. There we go. So we've established everything about that motion now. We've established how far it will go, how high it will go, and how long it will fly for. Yeah? So let's finish with the hardest scenario, which is the old classic firing an arrow up and it landing down and travelling a amount of distance. Okay, I'm actually going to do that in a separate video because my iPad's running out of storage space, so I'm going to upload some videos and then delete some.